Okay, so today what I want to talk about is the concept of differentials, which really, I don't know how new this will feel to you. We're going to basically take some concepts and smush them together. Okay, what I want you to keep in mind is that anytime you see linear approximation, it really just means use the tangent line to approximate a value, okay? Linear approximation. We draw a tangent line to a curve, and on that line, we use it to approximate a value, okay? So when you're in calculus, that's what I want you to think about, okay? Now, if I were to draw a tangent line to a curve, okay, so I have this red curve, y equals f of x, and I have this tangent line in blue, and I'm going to call that tangent line L, L for linear approximation, okay? So let's talk about what we do to create a tangent line, okay? First of all, we find that our slope is the derivative, right? So our slope is f prime of that value. In this picture, it's a. And then we have the coordinate a comma f of a. Okay, this is like one of the first things we did, right? Now, if I wanted to write the tangent line equation, we've been using point slope form. Y minus the y value, in this case f of a, equals slope times x minus a. All right. Well, using our derivative, we know that our slope is really f prime of a. So if we were to solve for a, we would essentially just add over that y value, f of a, and all I've done here is I just changed y to be the L of x for linear approximation. Okay? All linear approximation is writing the equation of the tangent line and moving over the y value to solve for y. Well, remind me who sits next to you. Oh, that's right. He's going to be on me. Okay, thank you. Hi, Trevor. He'll be watching this later. Hopefully he'll be watching it. In my 7th hour, we always give a code word to see if they really watch it. Should we give a code word? No? Yes? You gotta give me a code word, otherwise.
Pineapple.
Code word pineapple. Okay, so we'll see if he really watches it. Okay, so find the linear approximation of f of x equals radical x at x equals 4. Okay, all this is asking us to do is write the equation of the tangent line and then solve the long. Okay, so go ahead and write down what information you need. Okay. Equation of a tangent line. We need two things. We need point and we need slope. Which one would you like to work on first? I hear slope first. So our derivative. The derivative of square root of x. CJ, what would that be? You agree with CJ? Okay. X to the 1/2 becomes 1/2 x to the negative 1/2. So he's just rearranged it. Okay. So there's our slope, but we need it at the particular point. What is our slope? 1/4. Now we need the coordinate. If x is 4, what's our y value? Say louder. 2. So if we write the equation of our tangent line, we have y minus 2 equals slope times x minus 4. Okay? And the only difference thing that we are doing is we are adding over that 2. And I really don't care if you add it to the beginning or the end, just add it over to the other side. Okay? This is our linear approximation. Now, why or how could this be helpful? Yes?
It's supposed to be 1/4, right? Not 1/2.
Not really sure why I wrote 1/2. Good. Thank you. I think I saw this right here. And I just started writing. Okay. All right, now, how is this helpful to us? Okay, really, tangent lines are helpful if we don't have a calculator. Okay, what would happen if I asked you to give me the square root of 4.02 without your calculator? Would you want to do that? Okay. Not really. But what can we do? Well, we know that the tangent line to radical x is this at x equals 4. Okay? So that's the tangent line at x equals 4 for square root of x. Well, we have square root of 4.02. Okay? So what we can do is we can plug in what for x? We can plug in 4.02 because that's the x value for our function. Okay? And 4.02 is the square root of 4.02. Okay? So if we plug that in, can we make that calculation without our calculator? I have confidence that we can. What is 4.02 minus 4? 0.02 divided by 4. 0.005. Okay, so on our tangent line, our y value is 2.005. So what we've done here is we've said, well, the square root of 4.02 is approximately 2.005. All by using a tangent line. Now, we're fairly accurate. Why? Let me ask a different question. If I asked you to approximate the square root of 6 with this tangent line equation, would it be accurate?
No.
Not very. Okay, so why is this pretty accurate?
Because it's close to the x value the slope.
Okay, it's pretty darn close to the x value that is on our curve. We're going to be a little bit off, and we'll talk about are we too much or too little. But the closer we are to that actual point, we'll go back to this picture right here. The closer we are to this point, the closer we are to the actual function value, right? The further we get out on the line, the further we are away from the curve, okay? Now, let's talk about, are we over or under? So are we an over approximation or an under approximation? I'm going to give you about 30 seconds to talk about with your pod, are we under or over, and why do you think that is? Go.
Yeah.
And then you drop the square.
So like we're actually 1.005 by itself.
This value is 0.
So like you're around that 2.5.
Okay. How many of you think that we are too high? This is an over approximation. How many of you think we're too low? We're an under approximation. Okay. Here is the square root of x. Part 3. You said we were too high? Why?
Because 2.005 squared is around 4.025, not around the 4.03. So it'd be too high.
So you're saying, so you're like kind of working backwards here.
Yeah.
If we square the answer that we got, we would have more than what we started with.
Yeah.
Okay. I like that explanation. Did anybody talk about the calculus behind it?
I said like if you you've got the square root graph drawn and then you drew the tangent line at x equals 4 or like whatever it was on it, it's only going to be on that graph at that point, and everywhere else it's going to be above it. And so like if you looked at 4.02, the value for the like tangent line is going to be higher than the value for the actual curve.
Okay, good. Our tangent line sits above the curve. What is the reason for our tangent line sitting above the curve? What one characteristic makes this tangent line above the curve? Concavity. Since square root of x is concave down at x equals 4, or everywhere, but specifically at x equals 4, since square root of x is concave down at x equals 4, our tangent line is above our curve, which means no matter what, it's going to over approximate. Okay? If I had given you, y equals x squared, and we approximated somewhere over here like at 3, our tangent line is sitting underneath the curve because it's concave up, and we would be at under approximation. Okay? You are going to get that question more than once, not only like this week, next week, but in the coming weeks. So anytime I ask you whether your tangent line is approximating over versus under, I always want you to think about concavity. Okay? I really liked your explanation, Will, but it's not going to work every single time. Okay? You might have like 145 that you really don't want to square to make sure that it gets back to the same thing, right? So the tangent line and the concavity is the easiest thing to look at there. Okay? All right. A really big picture going on right here, and this is in your book. Let me figure out what page it is in. It is on, so that you don't have to draw it. Okay. I looked at it just this morning. I can't even remember what page it was on. Yeah. 232. Okay? Because I don't think that you should really have to draw this in your notes. I mean, if you want to, you can, but page 232 is where you can find this in your book. Okay? So I want you to just kind of take a look at that picture right now. Okay? We have a curve and we have a tangent line. And what we're going to talk about is the concept of differentials. Okay? So, dy dx. dy dx. What does dy over dx stand for? derivative, it also stands for d. Okay. More specifically to that pink part of the picture. Okay. Think back to, you all are telling me the correct things, but there's one more synonym that I need. Slope. The easy synonym, right? Slope, okay? dy over dx is describing the slope of the tangent line, okay? Which is, yes, the instantaneous rate of change. Yes, change in y over change in x. All of those wonderful things, okay? But most importantly in this picture, it is the slope of the tangent line, okay? Well, what if I want this change in y right here? Okay? We can very easily find, we can take a coordinate on our curve, find the tangent line, and then use that tangent line to approximate the curve. Well, what if I actually want that point right there on the curve? Okay, how do I know what that delta y is, that change in y? Okay, so Eric, we're actually going to say change in y over change in x for delta y and delta x. And in this case, they are not the same. Delta x and dx are always going to be the same. But as you see in my picture, dy and change in y, those are two different values. Okay? So, how, using this picture, can we calculate delta y? How do we know what that length is right there? Okay. We're going to know x, and we're going to know what the change in x is. Okay? And we're going to be able to use that tangent line to figure out what that height is right there, right? Okay. Here we go. Do we know what this height is right here? What is that height? It's a, which is just f of x, right? If this is x, then this height right here is, like this is x, f of x, right? So this height is f of x, all right? And we know that this right here is dy, right? Right now I'm going to write this right here. Okay, if we know our function, right, if we know our function, we can take this height, f of x plus delta x, subtract out the f of x, and we have that change in y, right? Now that seems really obvious right now. Obviously that's the change in y, okay, but we're not always going to have all of the pieces of information to find it. Okay? So this is what we need to know about this picture. Alright? Here's what you need to write down. Delta x and dx are always going to be the same thing. Change in x and dx are always going to be the same thing. They're interchangeable. Okay? Their values are the same. As in that picture, delta y is the actual change in y of the function from x to x plus delta x. It's the actual change in y of the function. As opposed to dy is the change in y of the tangent line. I'm going to go back to my picture momentarily. I'll come right back. But as you can, I'm going to erase all of this nonsense tonight. Okay. So delta y is the change in y on the curve versus dy from here to here is the change in y on the tangent line. Okay. Now, do you agree that dy dx means the same thing as f prime of x? You agree with that, right? Well, now since we're working with differentials, we're basically taking dy and we're separating it from dx, all right? Then we can take this and we can write that dy equals f prime of x times dx, okay? We basically take that dy over dx and we move that dx to the other side, like we multiply it over. We separate the two differentials. Okay, and this seems obvious, but I still want to talk about it. If there is not a change in x, then dy and delta y will be the same because we're not moving along the curve or tangent line. We're stuck at that same spot. At x, okay, if we don't move, x is both on the curve and the tangent line. All right. So we are going to do basically the same example that we did with our tangent line equation, but we're going to do it now with this differential thing, okay? So we are going to let f of x be square root of x, at x equals 4, and our change in x is 0.02. Okay, everybody, dx would be what? Delta x, which is 0.02. Delta x and dx are the same, so dx is 0.02. Okay, now, this is differentials, which means it relies on the derivative, okay? We've already talked about the derivative of this function, right? We know that f prime of x is 1 over 2 radical x. Is that correct? We found that way back at the beginning of the lesson. Okay. So, when we talk about dy, okay, remember back here on this slide, dy is f prime of x dx. We basically take dy dx and we separate the dy and the dx. So, dy is f prime of x dx, which in this case means dy equals 1 over 2 radical x dx. So, dy, our x is 4, and our dx is 0.02. What's dy? Say it louder.
0.005.
Oh. Okay. What did we just find? Okay, well, we're almost there, right? This is basically saying on the curve, our change in y, well, on the tangent line, right, our change in y is 0.005. Okay? Essentially, we used a tangent line without writing the equation of a tangent line. So if I wanted to approximate the square root of 4.02, it would be approximately 2.005. Let's talk about why that is. Okay, we already knew that from our first example, but essentially we added 0.02 to our x value, right? And when we add 0.02 to our x value, then on our tangent line, the height changed by this much. So if the height at 4 is 2, then the height at, when we change x, we're going to change y by 0.005. Okay. Without using a tangent line, we use a tangent line. Okay. Now, with a calculator, if we wanted to actually find delta y, well, delta y would just be the change in our function values. So in this case, what is the difference between the function value at 4.02 and the function value at 4? Okay? Well, the whole point of differentials is that so we don't have to use our calculators. But if you actually took the square root of 4.02 and the square root of 4, they would differ by 0.0049, blah, 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 blah. Okay? Pretty darn close to what dy is. dy and delta y should be pretty close. Okay? We know that dy is more, though, because of that over approximation we talked about in the beginning. All right, so let's focus on just the differentials piece. Okay? Go ahead and write this one down, please. Okay, so it's giving us that delta x dx, I'm going to call it 0.01. So our change in x is 0.01. All right? What is the derivative of 4x cubed minus 1? 12x squared. That's a nice one, right? So what we're going to write is dy equals 12x squared dx. Okay. So now all we need to do is x is 1 and dx is 0.01. All right. Well, 12 times 1 squared is 12. Times 0.01 would give us what? 1.2. 0.12. Why did I write 1.2? No. There we go. Now, what does this mean? Along the tangent line, from 1 to 1.01, there is a change in y of 0.12. Okay, so let's kind of process that. If I were to plug in 1 into our function, what would we get? We would get 3. So this means, since our change in x is a positive 0.01, we are approximating 1.01. We move 0.01 away. Okay? And when we do that, our dy was 0.12. So if we plug 1.01 into our function, it is approximately 0.12 more than the original function, than f of 1's function value. Delta x 0.01, dy 0.12. Should we get some science thrown in here? I'm sure you guys are like motionless. How many of you like science? I know some of you science is your favorite subject. Yes. Okay, let's get some science thrown in here. Okay, we can actually use differentials to approximate the error in computing different things, but in this case, we're going to calculate the error when computing the volume of a sphere. Okay? Computing the volume of a sphere if the radius is measured to be 10 centimeters. And I want my error to be either plus or minus 0.2 centimeters. Okay? I can be off by 2 centimeters, either more or less. Okay? Let's talk about what they gave us. Volume of a sphere. How do you calculate it? Pi r squared? Cubed. Okay. Unrelated. Do you notice how the derivative of this would be the surface area of the sphere? I feel like that's a really cool connection. Anyway, back to our topic. Plus or minus 0.2 centimeters. What did they give us there? Okay. Change in x. Now I'm going to call it the change in r because I wrote my function in terms of r. Okay. If you want to use y and x, that's fine. But since it's volume, I'm going to use v for volume and r for radius. Okay? So we're going to do the same thing. We're going to use our differentials. Okay? Now we know that the derivative of volume with respect to the radius would be 4 pi r squared. Do you agree? Okay. So what we're going to do for our differentials, we're going to say dv equals 4 pi r squared dr. We're going to separate the dv and the dr. Okay. Now we want our radius to be 10 centimeters, and it is okay to have an error of 0.02. Okay? Now remember, the whole point of this is so that we don't use our calculator. If we had our calculator, we wouldn't need a tangent line. Okay? So what is 10 squared? Times 0.02 times 4. So we have 80 pi. And remember, this could be plus or minus. Kind of forgot about that when I wrote that in there. So we could be off by 80 pi cubic centimeters. Yes?
100 times 0.02 is not 2% of 100. This is 20. So it'd be 8 pi.
Hold on.
Is our error 0.2 or 0.02?
10 squared.
So you both are right.
Oh,
Our error is 0.2. Our error is 0.2. I wrote 0.02. So someone was answering their 0.2 and I was asking 0.02.
Sorry.
No, that is my fault, not yours. I put my 0 after the decimal place instead of before.
So it's like the right thing.
Yeah, we're all right. Except Ms. Holman, I just wrote the wrong thing. Okay? Okay, Okay, so now how do we calculate our error?
Like percent.
Our, sorry, yes, our percentage error. Yes, this is our error. Okay, so we need to take dV and we need to divide it by our actual volume. So our dV was plus or minus 80 pi. Our actual volume would be 4/3 pi r cubed. Okay. We can do this. The pi's cancel. Got that? How many zeros are we talking about here? How many zeros are going to be down here? How many? 3 zeros. But only 1 here. So we're going to have 2 decimal places. And what is 8 divided by 4/3? 6. Okay. So we are going to have an error of 6%. Okay, if I remember right, your assignment is not very long. Okay. I really only have like one concept that we talked about today. Okay. They're short problems compared to what we've been used to, right? We kind of had some long problems with like optimization and curve sketching, all that stuff. Tomorrow, Thursday, our last 2 days of notes, and then we study for that chapter test, unit test, I guess I should say. Now, for some of you, this unit test is going to, I don't want to say make or break your grade, but if you're on the edge of a grade, this unit test is pretty important. Okay, we only have 3 unit tests. If you're worried about what you need to get on this test, take your previous 2 unit 2 tests, find that average. You have to score higher than that average if you want your grade to raise. So if your 2 tests have been an 80 and a 90, that averages to an 85. This test would need to be above an 85 if you want to see a positive change in your grade. Does that make sense? All right. I do have some things I need to hand back to you. So I'm going to take this time to do that.